Looking back on our giant box of definitions and notes regarding variance and standard deviation, hint, 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 all of it should go on a note sheet perhaps, hint, hint. Remember this important bit down here when we talk about interpreting the standard deviation. We said at the time that most data falls within a standard deviation or two of the mean. I want to get a little bit more clear about what most means. Now, in random data sets, it can be somewhere around 50% to 60%. It just depends on the data set. But we want to get a little bit more precise with it for a very particular kind of data set that is bell-shaped. So let me scroll down to the empirical rule. The empirical rule is kind of analyzing what that most means. And it's saying if the distribution is roughly bell-shaped, i.e. normal, in other words, it has this shape that you see right here before you. If it has that shape, which is a big if, because lots of data sets do not have that shape, but if it does, then approximately 68% of the data will lie within one standard deviation, 95% of the data will lie within two standard deviations, and 99.7% of the data will lie within three standard deviations of the mean. So when you think back to that definition box, we said quote unquote most of the data. So I'm refining that a little bit and saying, hey, if you know it's bell shaped, then most is actually 68% of the data will lie within one standard deviation of the mean, and 95% of the data will lie within two standard deviations of the mean. So before I go any further, let's analyze those percentages. So here is the normal curve. 68% cut two ways because of course the graph is symmetric is 34 and 34. So 34% to the left of the mean, between the mean and one standard deviation below the mean, so mu and mu minus 1 sigma. And there's another 34% between mu and mu plus 1 sigma. So together those make 68. If I add up the 13.5%, the 34%, the 34%, and the 13.5%, those four numbers would get me 95%, which is where the 95% comes. And then 99.7 would be all of them except for the little tail over here, which is 0.15%. Be careful, that's not 15%, that's 0.15%. That's less than 1%, so it's very small. And the other side also has a 0.15%. 0.15 and 0.15 together make 0.3, and that's why the rest of it is 99.7. Now, before I go any further, let me just make sure that it's very clear that this is only for bell-shaped distributions. If it's skewed right, this does not apply. If it's skewed left, it does not apply. If it's bimodal, that's when it has like two peaks, kind of like a camel's back. This does not apply. There's all sorts of graphs that it does not apply to. But if it does apply, then these percentages are roughly what they should be. Now we're going to get more fine-tuned with those in Chapter 7, but for our purposes for now, that's fine. Okay, so now I've drawn this curve by hand and it's also on your exam notes packet. So you don't actually have to recreate this curve here or on your notes packet, but you will perhaps have to recreate it on an exam or a worksheet. So let's take a moment and just kind of look it over real quickly. The x-axis has to be drawn and it's a horizontal asymptote. So the x-axis is the horizontal line at the bottom and the curve gets closer and closer to it but never crosses it. That's what it means to be a horizontal asymptote. The graph is symmetric, which I already said. It's symmetric, meaning even mirror images on either side of the mean. So the mean is actually a center line and it's symmetric on either side of that. That means that the mean will be the vertical line down the center. Now, this particular example here, I've given you mu, but keep in mind it could also be x bar. It kind of doesn't matter. So either you're working with a population, so it'd be mu's and sigmas, or you're working with a sample, it'd be x bars and s's. But the theory still holds. Now, one standard deviation falls at the inflection points. Now, what are inflection points? Well, the inflection points are right here at the where the mu plus 1 sigma falls, where that first vertical line falls after the mean and the other first vertical line falls before the mean. There they are. Now you know this point physically. If you've ever been on a roller coaster or if you've ever been in a car that's hitting a hill too fast, it's where your butt kind of lifts up off the seat, where you feel that rise of your body off the seat. That's the inflection point. In calculus, it's where the second derivative is 0. But if you've never taken calculus, don't worry about it. It's just suffice it to say it's where you're going the fastest. So if you're on a roller coaster, that point is where the roller coaster is going the fastest. And then it starts slowing down after that, believe it or not. So that's what the inflection point is. It falls about a little bit above halfway. So if you look at the x-axis on the bottom, the peak at the top, it's just a touch above the halfway, because halfway would be right about there, and it's just a bit above that. And that's where it will always fall on a normal curve. So you place vertical lines at each inflection point, right? The inflection points, visually, this is how you find them. They fall, they're vertical lines that fall just a touch above the halfway from the x-axis to the peak, right? So you put those lines at a spot that's just above halfway. So halfway is a little bit lower, then you come over here and put it just a little bit above, and it has to be symmetric. So it should be the same distance on the left and the right. That's very key. Speaking of which, that's where you lose points. So you keep your lines vertical. They should be straight up and down. They should be perpendicular to the x-axis. All these lines are straight vertical. And keep your spacing even. That's one of the most important points, because whatever the standard deviation is, let's say it's 10. 10 units is in that from the mean to the mean plus a sigma. Then there should also be 10 units from the mean plus 1 sigma to the mean plus 2 sigma. Those widths of the white zone and the gray zone and then the dark gray zone are all exactly the same. If they're not the same, then you're going to lose points, right? So you got to keep your spacing even. You got to label each section with the appropriate percentages, and then you label your vertical lines with the appropriate numbers. And above all else, become a good guesser, if you will, of where the inflection point falls. You need to be able to eyeball that reasonably. It's not too tall, it's not too short, these sections in the middle are not too skinny, right? And these little tails over here should be really tiny. If you've done it right, there should be really small amounts in the 0.15 tail. In other words, it should look like this picture. This picture is drawn by computer. This is what it should look like every time you draw a normal curve, more or less. And a lot of the times I draw the curve for you, as I do in the next example, and I expect you to fill it all out. So here's the normal curve. Let's read the problem. It says, in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the U.S. was 64 inches with a sample standard deviation of 2.75 inches. Assume the heights of women are normally distributed. See that? That means that we can use the empirical rule. Great. So we will do so. So you draw a center line down the middle for where the mean is. Then you eyeball the inflection point at about a little bit above the peak, and then you keep going and going from there. I've got it all drawn by computer, right? Center line down the center, and then you make sure that your inflection point falls appropriately. This is what an inflection point looks like. Again, I take halfway and go just a little bit above, and then that's where I draw my line, and then I draw it at the exact same spot on the other side. The graph should be perfectly symmetrical, so that the lines on the left and the right of the center should be exactly the same distance. So this, in other words, the 61.25 is the same distance away from 64 that the 66.75 is. The 58.5 is the same distance from 61.25 as is 64, right? It's all equal, equidistant, I should say. All right, make sure that when you do this, again, inflection points are drawn, spacing is even, put out every single percentage, put down every single number. So 64 is the middle. Then I add a 2.75 because that was my standard deviation. So 64 plus 2.75 will get me 66.75. When I add another 2.75, that gets me 69.5, and so on. Here, let me prove it to you. 64 plus 2.75, enter. Then I add another 2.75. And then I add another 2.75, and then I'm done. I stop at 3. Now keep in mind, this 0.15, let me just scroll back up here. I was more clear about it up here. Those are arrows. That means that it goes on forever, hypothetically speaking. Now, we all know that women can't actually be, forever tall, but it doesn't matter. This is a model. So you're saying anything past 72.25 is 0.15% of the population. So anything, women that are 74, 75, 76, 77 inches tall, they're all in that 0.15%. Similarly, 54, 53, 52, 52 and a half, they're all in this bottom 0.15%. All right. The hard part about these problems is getting this all down, getting it so your spacing is even, your lines are at the inflection point, everything is nice. So draw the center line first, draw the inflection points next, draw their vertical lines, then keep that spacing even for the next line over and the next line over, and so on. Then put in all your percentages, but you never have to worry about those because they are given to you right here in this picture, and that's given to you on your exam notes packet in the back of the course pack. So that will be given to you in every exam. So you don't have to memorize that, you just have to use it. So you know what those percentages are, just write them down in their appropriate areas. Double check for yourself. Does the 0.15% look really teeny tiny? It should. Does the 34% look really nice and big? It should, right? Once those are in, then all the rest of the questions are easy. So what percentage of women are between 64 and 69.5 inches tall? Well, 64 is the middle line, so between 64 and 69 would be 34% plus 13.5%, so that's about 47.5%. Now don't worry about the estimation. Do not round this. So let me make a note. Note, do not round. Right? Don't round it up to 48%. Right? Use the empirical rule percentages as given. There we go. So I know it says approximate and about, just live with it. Because if you remember, the rule itself is approximate. So don't over round it, right? Use the percentages that are given and don't round them. All right, now what about the women that are taller than 69.5? Well, that would be the 2.35 and the 0.15%. So that would be 2.35 plus 0.15 makes 2.5%. Again, do not round. Leave it. I know it's ugly at 2.5. We don't like decimals and percentages, but we're just going to have to get used to it because that's the way this empirical rule works. So leave it at 2.5%. Now, the percentage of women that are taller than 64, well, that would be half the curve. Now, let's think about this. The whole curve makes 100%, right? So if 64 is the middle line, then half the women are taller than 64. So there's no real work to show on that one. It's just 50%. I mean, it doesn't get much easier than that. So you might want to make a note that the whole curve is 100%. There. Since the whole curve makes 100%, then half the curve would be 50%. Now I know what you're thinking. You're thinking, well, what if a person is 64 inches tall? But remember, height is a continuous variable. People aren't actually 64 inches tall. They're 64.0236 inches tall. If we just had a good enough measurement tool to measure them, that's how it would work. So because it's a continuous quantitative continuous data, we actually don't have to worry about exactly 64 because it's sort of impossible to be exactly 64. Even if you were 64 inches tall, you'd be 64.000002362, right? We'll talk more about that later in chapter 7. Now, this is the trickiest of all, between 61.25 and 72.25. So that'd be 34, 34, 13.5, and 2.35, and we stop right there because it's between. You don't want to include the 0.15 because the 0.15 is past 72 inches tall. So we want to add up 34, 34, 13.5, and 2.35, and that leads us to 83.85. Again, do not round. Do not round that up to 84. I know it's tempting, but if you round it up to 84, you're including the women that are past 72.25 because that's the 0.15% that you're missing. So in empirical rule questions, use the percentages that were given in the rule and nothing else. All right, now our old friend unusual. What would be considered unusual? Well, let's remind ourselves what unusual is. That's back several pages. One sec. There it is. Okay, so for our purposes, we're going to stick with the two standard deviations rule at this point. This rule down here is actually a little bit more for probability when we get there, which is chapter 5. So just hold tight on that one. So we want to look at being beyond two standard deviations. That'll be unusual for us. So if you're very tall, above two standard deviations on the high side, or very short, below two standard deviations on the low side. So for us, that would be a woman that's above 69.5 inches tall, right? Because that's two standard deviations away, or below 58.5 inches tall, right? So either one, shorter than 58.5 or taller than 69.5, because they are both, let me put it this way, they're both beyond two standard deviations. Remember that 69.5 and 58.5 themselves technically are not unusual, at least not by this definition, this rule of thumb. It's beyond 2, so taller than 69.5 or shorter than 58.5.